So therefore, it is a great pleasure and an honor to have Professor Giulia Galli from the University of Chicago and Argonne National Laboratory giving a talk today. She has done very important work and pioneering contributions in different aspects of condensed matter physics, material science, quantum information, and other areas, computational physics. And then she has done important work. And then today she's going to be talking about embedding theories for quantum simulations on hybrid classical quantum architectures. Thank you for coming here.
Thanks, Franco, and thanks everybody for inviting me here. And you know, it would have been great actually to be present in person, but it just didn't work out with the imminent start of the quarter. But I hope to be visiting at some point. So what I would like to do today is tell you about a development that we have made in our group to study basically a highly correlated state of spin defects. And I want to tell you why we got interested in spin defects. And basically the reason is that we want to be able to predict properties of this system for their use in a quantum information application. And this led us also to develop a classical quantum protocol to carry out quantum simulation and also to understand how to mitigate noise and errors on near-term quantum computers. And before I start, I would like to point out the people really who did the work and also some papers that you may be interested to look at. And this work was initiated by my grad student Mahe, who is now working at Google, continued by grad student Wenchen Wang Nansheng and postdoc Christian Forwerk, and staff scientist at Argonne Marco Covoni. And I will also mention work done by postdoc Sija and grad student Eugene. Okay, so let me put this a little bit in perspective. We are broadly interested in defects in semiconductors to realize qubits. Basically, to realize two-level systems that we can address, for example, optically, and harness the power of quantum information for computing, sensors, and communication application. And optically addressing a two-level system means that we want to understand the transition from the ground to an excited state, followed by a spin-selective decay path with non-radiative transition. And here I am showing the picture of the energy level and also the cartoon of one of probably the most famous spin defects in an insulator, which is an NV centering diamond, a missing carbon atom and a substitutionally nitrogen atom charged negatively. So if you want to study this system, actually you need to be able to study multiple properties of spin defects if the application you are interested in are those that I just mentioned. Certainly the electronic properties here, I have another defect that I will mention. It's a double vacancy in silicon carbide. And sometimes you do know what are the defects that people are interested in, but sometimes you don't know how they form, and you would be actually interested in predicting free energy surfaces and how these defects form. And we have done some work recently on this by coupling first principle MD and advanced sampling method. Most of our calculation always start from density functional theory, but it turns out that the sum of the defect actually do have highly correlated states. And it is the many-body states and it is the correlated neutral excitation that are really the important physical quantities if you want to understand how to address these two-level systems. And then, of course, you want to know how they emit, for example, compute photoluminescence spectra. And finally, because this is what we are after quantum information application, you need to understand coherence property, qubit coherence times. So in order to do that, of course, you need to be able to couple several quantum mechanical methods, starting from DFT with quantum embedding theory, which is what I will talk about today, time-dependent DFT, and finally also use spin Hamiltonian with ab initio parameter to look at coherence time. So let me tell you about our development on quantum embedding theories. And at the very end, I will also mention briefly some work that we have done on spin coherence. So as I said, when you look at defects in semiconductor and insulators, basically most of the community starts from either density functional theory or hybrid DFT or many-body perturbation theory, for example, GW. And these are very useful and for some states, accurate or semi-accurate methods to predict the properties of many defects. However, there are defects, there are states, even on defects that are apparently simple, like the NV center, or more complicated defect having transition metal ions that are highly correlated. And they cannot be described by just a single Slater determinant that require a level of theory beyond density functional theory. So what we have done, and I mean, many people are after this problem, and there are many methods in the literature after this problem, and I'll tell you our take on this. What we have done, we have considered the full system, which is the full solids with defects in it. And then we have used a low-level method for the full solid. And low level, I mean either density functional theory or GW. And then we have found a way of embedding the defect in this solid using a higher level method, for example, configuration interaction. Every time you do any kind of embedding, you need to take into account double counting terms, the terms that are there both in the parts that you have embedded and in the full solids. So the method is based on ideas that, a long time ago, more than 15 years ago, were put forward by Ara Setyan. They were kind of not of course, in their implementation close to what we do today, but there were some ideas based on Green's function in this paper and also in the paper of Bergstedt 4 years ago. And down here, I'm describing our papers and how we do our implementation of this embedding. So the there are two kind of original ideas. One is how we compute the dielectric screening of the host and the effect of this dielectric screening on our embedded defects. We compute it with algorithms that we have developed in the last 10 years to do many-body perturbation theory calculation. And these algorithms are such that we could scale this calculation to solids with hundreds of atoms. So people have used similar ideas before, but just for small system. And now we can do really hundreds. I will show you calculation with 500 atoms. And don't get me wrong, 500 atoms are for the solid. The embedded region contains a number of electronic states related to a smaller region. Although the embedding is not done in real space, the embedding is done based on the electronic states. We then derive an effective Hamiltonian that we can diagonalize both on classical computers and on quantum computers to get correlated many-body states. The other ideas that actually is in this work that we have just published, which is, in my opinion, very important. It's very technical, but very important. I will not explain the technicality, but let me at least mention this, is that when we derive the effective Hamiltonian, we found a way of removing the double counting that comes from having this region embedded in a big solid, exactly, provided the low level of theory is G0, W0. So 2 points, going back, the dielectric screening with algorithms that can be used with both the DFT and hybrid DFT, without computing any virtual states. This is what allows us to scale to hundreds of atoms, and a way of computing our double counting that is exact if the low level of theory is G0, W0. This is very important. Okay, so what do? We start from a DFT calculation. We define an active space by using specific localization function. We set up in Hamiltonian. All this is implemented in the open source code West. It has just been released, the version with the quantum embedding, and there are tutorials if you want to download it and try it yourself. And then we diagonalize, for example, full CI, the effective Hamiltonian with PySCF, the code maintained by Garnet Chen at Caltech. There is another thing we are really interested in, and it is the following question that we are asking. Can we learn the dielectric screening? Can we use machine learning techniques to basically come, starting from regression, to learn the dielectric screening for different configurations? We haven't done this for quantum embedding yet, but we have done it for other properties like optical spectra in this work, and the first author is Sijia Dong, but I won't talk about this today. So there are many embedding theories, and we have written recently a perspective by comparing what we are doing based on Green's function to DMFT, and also relating our formulation to, for example, density matrix embedding and other embedding theory. Okay, so results. Let's look at the NV minus in diamond. We start either from DFT calculation based on semi-local functionals, for example, PBE, or hybrid functional, for example, DDH. We choose the active space with the localization function that I told you about before. And so these bars here are the energy of the states, single particle orbitals that are part of our active space. And then we compute the energies of the many-body states. This is the central panel here, as a function of the number of atoms that are present in the big, in the environment, and we converge them. This is now why it is so important to see that we are able to do calculation with 500 atoms to really converge our calculation. And these are our results. This is experiment. These are our calculation, and of course it is better than GW and BSE because these are correlated states, and it is somehow comparable to some CAST-SCF quantum chemistry method, which, however, were done on clusters. It's not perfect, but it is, a real qualitative success, and also something that can tell you about the physics of the many-body states of the system. So is everything solved? No. So this is a defect that, this is a charge defect, this is a neutral defect, and this is apparently a defect that we thought we would be able to handle. And again, we were able to converge well our calculation. We were able to have also large active space. And there were other calculations that were done, for example, with the MET and other embedding theories. And, qualitatively, we kind of all have the same trend, but we all disagree with the experiment by 1 electron volt for one of the states. And this is still under investigation, and we don't understand. And we have actually a project specifically in collaboration with my colleague here, Laura Gagliardi, who is an expert in the MET, to understand what's going on. So one question is, do we have the right geometries? Do we have the right geometries for this system? Is the geometry a problem for us? So we also carried out a project to compute optimized geometries in the excited states. And we have done this only for the NV minus in diamond right now. And we have done so with the spin flip time-dependent density functional theory with hybrid functionals. So the work is under review right now. And the first question is, okay, with spin flip TDDFT when you compute your geometry, so you only have single excitation. Are these single excitations enough compared to your QDET, where you also have doubles and others? And we compared TDDFT spin flip with QDET at fixed atomic position, and we did find a qualitative agreement. Full quantitative agreement can be obtained only perturbatively, by perturbatively adding on top of TDDFT the double excitation, and we did so. But the qualitative agreement, actually almost quantitative, is pretty good. So we use TDDFT with spin flip to compute absorption spectra between strongly correlated states. Please note these states here, 1E and 1A, these are group theory, C3V nomenclature, but it doesn't matter. What matters is that this is an absorption spectra compared with experiment between highly correlated states. And now we can really get things right. We can get things right for all the peaks and not only for the zero phonon lines. And of course, we need to have our QDET to make sure that at least at fixed atomic positions, we get all the excitations correctly. All right, so now that we have an effective Hamiltonian, we can also, so by the way, we haven't, just to make sure, we haven't solved yet this problem. We are looking at this problem right now, and we are computing spectra, and we are doing a lot of work. It's just to tell you where we stand. I mean, these are very new things. So, okay, so now we have our effective Hamiltonian here, this effective Hamiltonian, and have just presented results to you for an effective Hamiltonian that was diagonalized with full CI on a classical computer. Can we do a calculation on a quantum computer? So why would we want to do that? Well, you know, there is a promise that quantum computers would one day, at least when they become fault tolerant, solve problems in a polynomial time. But even if they don't, which there is a lot of controversy whether they could for quantum chemistry problem, maybe they actually allow a prefactor which is so much better that they would be advantageous. And so our take on this is, let's learn how to use these devices, even in the era where they are still noisy. So what we did, and this is a very complicated kind of diagram that I'm showing here, just to show you. So we do DFT, we do quantum embedding, we set up a effective Hamiltonian, then we do a transformation, either Jordan, Bickner, or others, parity transformation, to go from the effective Hamiltonian to a qubit Hamiltonian. We write a parameterization of the wave function, and then on the quantum computer, we do variationally quantum eigensolver and quantum phase estimation algorithm. The first, the upper part for the ground state, and the lower part for the excited states. So we have a big preparation on a classical computer, then parity transformation to qubits, and then we do calculation on a quantum computer. Okay, so first we do simulation of the ground state, and we take exactly the defects that I just showed you, VV center and double vacancy silicon carbide. Actually, I didn't show you the double vacancy, but we also did that. What do we find? We do calculation on IBM Casablanca. We use Qiskit, which is provided by IBM. And the very first thing that we found is that apparently, see, this is the minimization. 0 is the classical reference that we know we should obtain, and we are below. How come that a variational algorithm is below the expected numbers? The reason why we are below, it is because the quantum computer is noisy, and the Hilbert space of the qubit Hamiltonian is larger, and basically the noise does not preserve the constant number of particles that we start from. On the classical computer, you have n electrons, and these n electrons never change. But on a quantum computer, because of noise, we actually pick up on physical states that are states with a different number of electrons included in the simulation. And then all bets are off, right? Because the variational quantum eigensolver is not variational anymore because there is no constraint on the number of electrons. So we have to add a constraint on the number of electrons. And actually we did this. Is not the most elegant way. Now we have a better way, but in the paper that we published a few months ago, we did this by post-selection. So we do a simulation, we have all the states, and then we run a script where we post-select only the states with the right number of electrons, and we restore, orange, the variational nature as it should be of our algorithm. So this is the first thing that we did. However, this is not enough. It's not enough because you do converge, you are variational, but you are above by quite a lot, above the reference state, the classical, you know that reference state. And by quite a lot, I mean by a number that is maybe 10, 20%, that if you didn't know the right results, would not allow you to have a good physical interpretation of your system. So we came up with zero noise extrapolation techniques. And again, this is a little bit technical. It's in this paper, PRX Quantum, that we published a few months ago, where we boost the noise in a certain way without affecting the error that we have in our ansatz for the wave function, the Trotter error. And then we extrapolate. And you see here, the extrapolation actually works beautifully. And we then remove a majority of the noise coming from the device. So if you combine these two fixes, that's what we get. So state under the column state, you see energy differences between states that, again, they are, using the group theory. It doesn't matter. These are just excitation. Full CI is in a classical computer, a QC on a quantum computer without noise mitigation, and the yellow and green are with different noise mitigations. And you see, we actually get quite good results. I mean, not perfect. There are some degeneracies that still are not quite reproduced, but the results are now good enough that if we did not have the classical results, and if we just use the quantum computing results, we would be able to make a good physical prediction on our system for the states that matter. Okay, so what about other more complicated defects? For example, this is another defect. It's a negatively charged silicon vacus in silicon carbide, and the wave function is more complicated. Can we do it? Well, if you look at the number of CNOT gates that you need with the ansatz that we use, I didn't tell you exactly what we use, it's called UCC. The answer is no, we cannot do it. It's way too large. We don't have enough qubit, and even if we had enough qubit, the noise would kill us. So this is brand new work based on the work of Ismailov in Canada. We actually change our wave function ansatz, and now we map not, we map on Pauli entangles, we map excitation. So we do not do the mapping, the Jordan-Wigner mapping. Anyway, this is again technical, but just think about the fact that there are ways to reduce the circuit depth and to reduce the number of CNOT that you get, and then you can do your calculation. And we are about to send in a paper where we combine this new way of mapping the excitation onto Pauli correlators with our noise extrapolation techniques, and also with a new way of imposing constraint that actually allows us to do calculations that are much more complicated. Okay, so I am actually very close to the end of my talk, and I would like to point out that once you have figured out the electronic structure, and I showed you a part of the electronic structure for the many-body states, you also want to know about, for example, emission properties. This is this part here. But then the fun really starts because you want to know the coherence property of your spin qubits, right? Because this is what you need to understand if you want to use it for quantum information application. And here, before I close, I just want to point out two papers, a review paper that we wrote during the pandemic, and a paper that was mostly really all done by our collaborators in Japan, Kanai and Hideo Ono, where we looked at spin coherence for 12,000 hosts. And here we looked at specific guidelines for solid state qubit, taking everything into account, electronic structure, spin coherence, and so on and so forth. And in these two papers together, we identify new materials, including oxides, that could be good materials for quantum information applications. Okay. So I think that I've at the end of my 25 minutes, I would like to again show the name of the people who did the work, grad student Ben Chen and Nan, postdoc Christian, and the scientist at Argonne, Marco Govoni. Our work is funded by a Computational Material Science Center, funded by DOE, also Hub QNext, and by DOD Air Force. And really everything is done either in collaboration in terms of paper, but in collaboration above our discussion for sure with David Ashalom and Joe Harrimans in Chicago. All right, thank you so much. And again, thanks again for inviting me to speak here. Thank you.
Thank you very much for a very nice talk. And then people are welcome to type questions in the chat. I would like to focus on the results on the constraint on the number of electrons. So therefore, you were getting the energies below the ground state. And then, so you had to impose a constraint to avoid going down. This reminds me what happens in the when people do like the lamp shift. The reason why there was a lamp shift is because the system in QED can actually pick up extra photons from the vacuum, and so when you go beyond the rotating wave approximation, the number of excitations is not conserved.
Oh, okay.
So therefore, this is the origin of the lamp shift, and that's why the people were able to go from normal quantum mechanics to QED, and that's why he got the Nobel Prize, because it was essentially validity to the fact that if you want to explain features observed in atomic physics, quantum mechanics was not enough. You had to go to quantum field theory, and then this can be seen also in the experiment by Haroche, Jean-Michel Raymond, and others on cavity QED. When you go from weak coupling to strong coupling, you can ignore the rotating, you can ignore the counter-rotating terms. So therefore, you don't have the Rabi model become James Cummings model. So this is what many people do in superquantum qubits. But if the coupling is very strong, then you have situations like the one you're saying, like in which essentially the number of excitations is not conserved. So you can actually borrow photons from the vacuum and donate photons to the vacuum. And this is, I thought it was like interesting. Of course, in your case, you're not in that regime, so you need to add a constraint. But this was like a interesting thing. Someday we can discuss separately, but it's
and you know, we in the very first paper that we did, because our model was so small, we didn't realize that it was almost conserved and there were some very tiny noise. But then when we increased the number of degrees of freedom, we saw it. And I think, you know, now I think we have a little bit of a better way of imposing this constraint, but there must be even better ways. And I think this is a problem that we have to really take seriously, because it will be here with us for a long time on quantum computers. That's yeah, but thanks for the comment. Yeah.
So I'm looking at the Okay, so when people type things on the computer, you're saying that the dielectric screening of the host needs to be computed beyond the random phase approximation because of this correlation. So therefore, like anything that smells like mean field theory or averages breakdown. So if you want to get a good dielectric screening, you need to add these correlations, no?
So, you know, we believe the dielectric screening is, so we will eventually need to verify that, but the dielectric screening, so the host is described in the weakly correlated limit. So we assume, and we have, you know, enough experimental evidence to show that if, as long as we don't have defects, other defects in the host, we can deal with the host at the mean field or G0, W0 level weakly. And so the screening of the host should be totally fine. In the,
for mean field theory, I see.
Yeah, but the states that originates from the presence of the defects are states that you cannot describe by just using one single Slater determinant. They are not single reference, they are strongly correlated, so you have to do something else. So we use the screening to actually define the effective Hamiltonian, but then the effective Hamiltonian we treat by describing the active space with quantum chemistry method that can account for the strong correlation of the defect. So that's and you know, there was a comment in the chat. I don't know who said that, but it's interesting. Somebody said, the director said maybe the experiment is wrong. The calculation agrees so well. I must say that we start actually wondering whether there is something in the experiment. Either there is a physical effect that nobody has included for that defects, or there is, because even when we consider the geometrical relaxation, I didn't show it here, but the correction is not 1 eV, it's minor, it's 0.1, 0.2, something like that. So we are starting to talk to the experimentalists to see whether other people can repeat those measurements. It may not be correct. But, you know, to be actually listened to by experimentalists, so when you go there and say, oh, maybe you're wrong, it's not that easy. So, yeah.
Julia, we have a couple of questions here.
Yeah,
so,
go ahead.
Hello?
Yeah, I'm here.
Yeah. So I want to ask a question. When you do the embedding, how do you choose the physical size of the core? Do you increase until it saturates, or?
Yeah. That's exactly a very good question. This is a very important question, and so the size is not the physical size in real space, but it is the number of single particle orbitals that I have to include in my active space. So so first of all, you know, I wanted to include a number. So the whole construct is based on the fact that I have localized orbitals around my defects. And this is not just an hypothesis that I want to do to make my theory work. It is because if you want to use these defects as two-level system embedded in a solid, this is what you physically want to realize, right? You want to have localized states. So the question is, how many of those localized states and resonant states do I include in my active space? And I count the number of localized states with this localization function. And then I do a convergence of the energy of my many body states as a function of the number of localized states that I include. And then when I include enough states, and you know, for some of the states, I am converged very quickly. For some, I need much more. But the convergence is done as a function of the number of single particle states that I put in my active space.
Hey, Julia, I have one other question. First of all, thanks so much for a very nice talk. I want to continue a little bit along with what Franco was asking about earlier. So of course you can only correct for these T1 errors in the terms of the Hamiltonian that only have I's and Z's in them. Can you discuss a bit the effects of noise in the terms that you cannot post-select in this way? Does that also give a shift of your final estimate, or is it a different effect? Do you know what I mean?
The remaining noise?
Yes, exactly.
Yeah. Yes. So the remaining noise, actually, you cannot probably, I should have a plot which is better here. So these energies are in electron volt, and the remaining noise, which is represented here by the orange curve, is not an innocent number, so it's not acceptable. So what if I actually just wanted to live with that excessive noise? I would get results for the physical energy differences that I want that would not allow me to have a good physical conclusion of my system. Okay, so this is why we actually went to a noise extrapolation. Let me explain. So we boost the noise in a controllable fashion, and then we extrapolate to get zero noise limit. So we do our calculation, and each calculation is a result of an average. You see there is an error bar, a measurement of average of many measurements on a quantum computer. Then we post a select, and then we have the orange curve. Once we have this orange curve, which is still too noisy, we boost the noise by doing basically a controlled expansion, a Taylor expansion of our noise. It's not that simple because we needed to do an exponential block replication for all the couple cluster type answers. But the idea is, look, you only have one data. You don't know how to extrapolate. So let's boost the noise a little bit and do the calculation for even bigger noise, which is the only thing that I can do. And then I extrapolate to zero. If you want to do that, you need to take care of a lot of technical stuff. And this is what this paper is about, PRX Quantum 2022. But if you do that, you can extrapolate really well. And then you get a number, which I showed here. These are the number extrapolated, which makes sense. Otherwise, they would not make sense.
I see. Thank you so much.
Sure.
Any more? Here I see on the chat, did you calculate for quantum gate processing time for elementary gate? Because quantum gate runtime and coherence time play a significant role.
I'm not completely sure. So calculate let me see if I understand the time. It's gone. The time that you, so are you asking me if the results depend on the coherence time? I mean, on the quantum hardware that I'm doing my calculation on? If this is the question, the answer is unfortunately yes. When we do our calculation, we do also a correction for noise as provided by the vendor, IBM. And all those measurements, you see those measurements that they are the error bar here of those measurements makes sense if all the measurements are taken on the same machine on the same day when the calibration of the noise of the machine is the same. If you do a calculation 3 days later and the calibration of the noise is different, you cannot mix the results. So we are far from the conditions that we have on classical computer when you can do your calculation today and tomorrow you use another computer and this is fine. Here it's not fine at all.
Hello.
Hi.
Hi. Thank you very much for your presentation. I'm interested about what the link you did between the ab initio calculation and the quantum physics. My question is, are you able to apply the same work you did on diamond on all other stuff made with carbon like graphene, graphite, and diamond? The result you apply on diamond can be the same with graphene, graphite, and diamond? I wish to know.
Yeah. So yeah, no, that's a good question. So the answer is not quite, in the sense that so if you first of all, everything here is a study of a defect. Maybe I should have made it more clear. Is a study of a defect or the energy level of a defects are in a gap, in the band gap of a semiconductor or insulator. So graphene doesn't have a gap, and that is, we cannot even start to look at defects in graphene with this theory right now, and also the screening, which would be a metallic screening, would have to be computed in a different way. However, if you do something to your graphene, or if you do something to, you do graphene, or you terminate, if you open up a gap, and there is a defect where the energy levels are in the gap, then yes, we can do that. But the initial assumption that I should have made more clear is that we are studying defects level that are within a band gap of an insulator or semiconductor. We have written a paper with a couple of years ago about also how to compute spin coherence time for 2D system. When you have a 2D system, things change for a number of reasons. So there are extra complications. Then once you are done with the electronic structure, there are extra complications for the coherence times, but they can be dealt with. They are not easy, but I think there is progress there too. Yeah, that's a good question.
Thank you.
Yeah, many thanks for everyone attending, and great thanks to Giulia Galli for a great presentation